This week, we're going to be taking a look at the same section, okay, every day, 2.4, and it's going to be on graphing. Okay, so we studied the 6 different trig functions, but what we've done with them is usually use them in an equation. Okay, this week we're going to draw pictures. Can someone just go through and quick remind me what's one of the 6 trig functions we've studied so far? Allie?
Sine.
Sine. Yep. What's another one? Yep, Brian.
Cosine.
Cosine. Yep, Brian.
Tangent.
Yep, tangent. Sine, cosine, tangent. And what are the other 3? Just one of them. Yep, Allie.
Secant.
Secant, and 2 more. Yep.
Cosecant.
Cosecant, and the last one?
Cotangent.
Cotangent. So there's 6 different trig functions. We are only going to study the graphs of 2 of them. The 2 that are up on the board, sine and cosine. Both of these graphs have a wave kind of pattern to them. The other graphs don't. All right, so what I usually do is I put up a picture of what the other ones look like, but we're not going to look at them too much. All right, so here's a picture of what sine and cosine look like. So if you look at those 2, they look pretty similar. Anyone describe the difference between the blue one and the red one? Or if you wanted to turn, say, the red one into the blue one, what would you have to do to it?
Shift of 1 unit.
Yeah, you just have to shift it, depending on which one you're looking at. You'd have to shift it to the left or to the right a little bit. That's all sine and cosine are. They're the same thing, except one is just shifted left or right. Now, if we look at tangent, you'll see this one looks nothing like the other 2. There's a pattern to it, but it's not connected. Okay, sine and cosine are what we call continuous. You can draw them without ever lifting your pencil. Tangent, you can't do that. You have to draw one section, lift it, put it back down, and then draw the next one. Secant and cosecant are similar. All right, so we don't study the tangent, the cotangent, the secant, or the cosecant. Okay, just the red one, just the sine and the cosine, the red and the blue. And basically what we're going to look at is the 4 different things you can do to the graph. All right, let me show you one example. So let's take cosine, and let's go like that. That's the original. And the one in red has been shifted up. So that's one transformation we're going to study, shifting it up and down, vertical. Another one we can do is we can shift it left and right. That would be horizontal shift. Let's take this, and let's do something like this. There's the original again. There's that one. That's a stretch or a compression. In this case, that's a compression. All right, so we took the sine wave, and it's like we squished it horizontally. So we can stretch and compress horizontally. That's the 3rd one we'll look at. And we can stretch and compress vertically. That'll be the 4th one. 3 out of 4 of those transformations that I just explained, I can show you something with sound about them. So if you think of like sound and like a sound wave, that's what a sound wave looks like. It's a wave, right? And we'll kind of learn what each transformation would do to the sound wave. Like how would you hear it if we did that? At least for 3 out of 4 of them. There's one transformation which doesn't really have a connection with sound, but the other 3 do. If you don't have a graphing calculator, that's fine. We're not actually going to be graphing on a calculator. We're going to just do it by hand, but I wanted just to kind of show you what they look like quickly. All right. Let's go back here. All right, so as I said, I'm going to be graphing transformations. There's 4. We're going to study 1 today, 2 tomorrow, and then we don't have class on Wednesday, so we'll do the 3rd one on Thursday. Now, before we can really start looking at how to transform the graph, we have to know a little bit about just the original. Like if you don't do anything to it, just the basic graph. So we're we're going to start by looking at some of the basic stuff about these functions, and then we'll look at specifically how you shift left and right today. Okay, just that one transformation. So this is what the two functions look like without any transformations done to them. You might have saw, like I would put in some numbers and it would make it look a little different. Like I put a +2 on the end, or I put like a ×3 inside, or something like that. If you don't put any numbers at all, that's what the basic function looks like as an equation. Y equals sine, y equals cosine. And these functions are very different than really any other function you study in algebra. They're not like a line, they're not like a parabola, they're not like any of those. These are called periodic functions.
Thank you.
Yeah. And what periodic means is there's a pattern to it. It means that once you know what one section of it looks like, you can predict what the entire thing looks like by repeating that pattern over and over. So let's take, let me get it even simpler. So let's look at sine. All right. So the first thing we'd have to do if we want to sketch it is kind of say, all right, well, we got to find one section and see what that looks like. And then we'll take that section and repeat it. If you start here and you stop here and you trace what I just did in red, that pretty much covers what this graph is going to look like. All you'd have to do is take that one section and keep copying and pasting it left and right forever, and you'd have your entire graph. All right, so you really just have to figure out what one section looks like. And between here and here is what we call it's a section. There's a better name, but for now I'm just calling it one section. And if you look at the y values, you'd notice a pattern. What we usually do is focus on certain parts of the graph. So you learned with a line, you really need 2 points to draw a line. Well, with this kind of graph, you need 5. Kind of have the beginning and the end, the middle, the highest, and the lowest. If you get those 5 points, you can make a pretty good sketch. You can get more than that, but you can't really do less than that. Okay, you really need about 5. And if you look at these points, this one is at 0. This one, and I'm talking about the y value, this one's at 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. You're going to keep seeing that 1, 0, -1, 0 pattern repeating over and over. And that's what makes this function periodic. The y values repeat over and over. I think that's what I have right here. So yeah, the y values repeat. And how do they repeat? They repeat over a certain width. That's what I'm talking about right here. That's the width that you have to travel before they repeat. And that width is something we have to figure out. So if I just bounce back to the picture for a second, that width is between these 2 black lines. Once you go beyond those 2 black lines, it repeats over and over, that 1, 0, -1, 0 pattern. But the question is going to be, what is that width? What are the x values start at, and what do they stop at before they repeat? If we can't figure that out, then we're not going to be able to graph it. Okay, so we have to figure out how wide one section is. And the width, or the length of that thing that I keep calling a section, is actually called the period of the graph. It's the width that you have to travel before the graph repeats itself. All right, I want to put another picture back up that I had earlier. It was the one where the graph looked like it was kind of squished together a little bit. Where was that one? Actually, let's go. No, that wasn't the one. That one. You know what? Let me just do it again. All right. So if you look at that graph in blue, the width that you travel before it repeats, that's called the period of your function. For the one in blue, it starts here and it ends here. That's what we call the first period of the graph, at least the first positive one. It starts here, ends here. Now, for the one in red, that's different. It's been squished. So for the one in red, it starts here and it ends here. From there to there is the first positive period. That width is smaller than the other one. Okay, the one in blue has a longer period. The one in red has a shorter period. Any question on that idea? Eventually, we're going to have a formula to figure out exactly how wide that is. Okay. Right now, we don't have to worry about that stretching or compressing it yet. Okay, we'll look at that more on Thursday. If you don't stretch or compress the graph at all, just a normal graph with nothing done to it, the period is 2 pi radians. And anyone remember what that's the same as in degrees? 2 pi radians? Uh, 180 would be pi radians. How many? That would be pi over 4. 360. So 2 pi radians is 360 degrees. All right, so let me put this back up. Let me just simplify that a little bit. And let's look at that picture again. All right, so what does that mean, 2 pi radians? Well, this is your x-axis. This is your y-axis. Your x-axis represents an angle. So if you were making a table, x column is an angle. The y column represents the trig function of that angle. In this case, it's either going to be sine or cosine. This one specifically is, that's sine. Sine of angle. So how would you actually use, how would you get a point on that graph? Well, we'd pick an angle. Let's pick, say, 0 degrees. The y column is when you take the sine of the angle. You take the sine of the number that you had in this column. All right, so if we take the sine of 0, let's see what we got. Sine of 0 is 0. That means that this graph should go through the point 0, 0, and it does. That's that point right there. Now, that point right there is the very end of the cycle. How long did we say the cycle is? Let's say it in degrees.
360.
360. So if you pick a 360, you should end up back at 0. Let's check it. Sine of 360, 0. So this 360 comma 0 is this point right here. And we have the other 5. Those are usually the ones that we use when we want to make a sketch. I'm not going to go through all 5 of them right now. But that's the idea. Your x-axis represents an angle, and your y-axis represents the trig function of that angle. The only two this week you have to worry about are sine and cosine. All right, so from here to here is 360 degrees, or 2 pi radians. Once you get beyond 360 degrees, you're going to be sketching something you've already seen before. The pattern is going to start repeating itself. And it repeats itself left and right forever. Okay, this wave never stops. It just continues forever. That's why when we sketch it, I'm only going to ask you to sketch one section. Because the idea is if you can sketch one section, you can sketch 2 sections. You can sketch 3. You just have to copy and paste what you've already done. All right. So this, I've already said to you guys a couple times. If you continue your graph beyond the end of the first cycle, it's just going to repeat itself. Just copy and paste what you've already done. Now, there is another name for a period. Actually, I think I just said it, and that's called a cycle. One period of the graph, you can also call it one cycle of the graph. I'll probably use those 2 words interchangeably. If I say to you, what's the cycle of this graph? What's the period of this graph? It's the same. But this word is used more often, especially in like things involving electricity. There's a certain measurement that says how many times does something cycle per second. And in electricity, that's known as hertz. Cycles per second. So if you look at a graph of electricity, if you have the right kind of tool, you can actually take it, you can plug it into an outlet, and it'll give you a picture of what the electricity looks like. Right? Not the kind of electricity in your car, that's DC. I'm talking about the kind like, in a building, like in this room, AC. If you graph it, it's going to look like a wave, the electricity. And it's going to go up and down, cycling 60 times per second. That's the standard way electricity works in the US. So you got to be careful. If you go to another country, most other countries run on 50 cycles per second. Well, what's the big deal? Well, if you like your device and you plug it in and it doesn't, have a way to know that it's on a different electricity, it's going to get, it'll probably just burn out. So you have to be careful sometimes when you plug things in other countries. If you look at like your adapter for your Chromebook or a cell phone charger, it's very small, sometimes it's hard to see, but if you look at that adapter, there's all kinds of writing on it, and it probably says something like this, 50/60 hertz, which means it's made to work on both types of electricity, whether you plug it in the US or you plug it in another country. Works on both. So we don't really use hertz in this class. When I talk a little bit about sound, I'll use that word, but other than that, we're going to stick to just using the word cycle or period. Those are the 2 words you'll hear quite a bit. All right, so this part I already said to you that in order to graph a trig function, you really need about 5 points. Some shapes are a lot simpler, and you don't need 5, like a line. A line, 2, good enough. But for a trig graph, you really need about 5. And I call these the 5 key points, or the 5 important points for a sketch. There's the first point, second point, third point, fourth point, fifth point. And what those 5 points essentially give you is the start, the stop, the middle, the high, and the low. If you know those 5 things, you can make a pretty good sketch of a sine wave. Now, in order to transform a graph, up, down, stretch it, shift it left or right, in order to do something to it, you have to know what it would look like if you didn't do anything to it. Okay, so we have to know what the basic graph looks like. So what we're going to do is we're going to make a table. And this table we're going to use every time we do a transformation. Okay, think of these 2 tables I'm about to give you as like starting points. It's what you start with, and then you're going to do something to the table in every problem. What you're going to do to it depends on what the result. What's the goal? Do you want to shift up or down? Okay, I'll teach you how to do that. Do you want to shift left or right? Well, that's different. I'll show you how to do that too. But you have to start with this original table. And we already started kind of making this table a little bit. I told you I wasn't going to go through the whole thing right then, because I'm going to do it right now. So the first point is 0, 0. It's the very first point in the table for the graph of sine. The next point is right here. That's called the first quarter point. Because if you put lines like this, that's the beginning. That's the first quarter. That's the second quarter point, which means halfway. The third quarter point, and then the fourth quarter. Well, that's the end. Right, so there's the point that's 1/4 of the way through the graph. Here's the point that's halfway through the graph, pi over 2, comma 1. That's this point. The next point is the one that's halfway through. And if we start at 0 and you end at 2 pi, what's right in the middle? 1 pi. And the coordinate of this point is 1 pi, comma 0. That's your third point. Pi, comma 0. The fourth point is right there. And that's at -1. That's the lowest that the graph ever goes, -1. And that's 3 pi over 2. And then the very last point is 2 pi, and you're back at 0. So those are the 5 points you need to sketch a sine graph. Now, cosine, remember that was pretty much the same graph. The only difference is it looked like it was shifted left or right a little bit. So if we put in cosine, and you look at those points, let's go like this. You're looking at this one, this one, this one, this one, and that one. Those are the 5 points we're going to look at to get the first positive cycle for cosine. So the y value is going to start off a little different. 1, 0, -1, 0, 1. That's the pattern in a cosine graph. Still uses 1s and 0s. It's just starting at 1 unlike last time we started at 0. Okay, so 1, 0, negative 1, 0, back to 1. And those are the y's right here. 1, 0, negative 1, 0, and 1. Now the x's are the same. The x's are exactly the same. Could you pick other x values? Sure. You could pick any x values you want. What's nice about these x values is they're the quarter points. The beginning, first quarter, second quarter, third quarter, and then the end. They're all nicely spaced. And that's the key with a lot of these graphs this week. You want to keep everything spaced even. I know in radians it can look like a little hard to see how these are spaced evenly, but if you change all these numbers to degrees, they are all 90 degrees apart. This is 0, 90, 180, 270, 360. Okay, any questions on those two tables? You really want to make sure you copy those right, because if you copy the table wrong, then every single transformation we do this week will come out wrong. So depending on what kind of transformation you want to do, you're going to modify one of these columns. If you want to shift something up or down, you're going to be changing y values. If you want to shift something to the left or to the right, that's going to be a change in the x values. Did everyone have the two tables? All right, so once we know the original table, the next step is, okay, you know where you're going to start, figure out where those 5 points are going to move to. They're going to shift up, they're going to shift down, they're going to shift left, right. You know, what's going to happen? Now, when we do a transformation in this class, we're only going to do one thing at a time. Meaning, if we shift it up, that's all we're going to do. We're not going to shift it up and left at the same time. That's two things. Can you do two things at the same time? Sure. Yeah, you can do 4 things at the same time. But in this class, we don't look at doing that many transformations in the same problem. So what that means is if we're going to only do one transformation at a time, when you take your original table, you only have to worry about one column changing per problem. You're never going to change both columns in the same problem. So either the x column is going to stay the same, and you're going to have to do something to the y's, or the y column is going to stay the same, and you'll do something to the x's. But again, never both columns in the same problem. That's why I wrote this. Any question on that idea? Of just doing one type of thing per problem, one transformation? Okay. So that pretty much covers, I would say, all the background stuff about sine and cosine. From this point forward, what we're going to do is look at one transformation at a time. And the first one we're going to look at is called a phase shift. A simpler term for that would be a horizontal shift. So this is the only type of transformation we're going to do today. take a graph, move it left, move it right. So what you're going to have to be able to do on the test is look at a problem like this, and you're going to have to know that's a phase shift. There's something about that equation that makes it a phase shift. That's what I'm going to show you right now. Okay, something about it that makes that a phase shift, say, versus an up and down shift. That would look a little different. Okay, but that one was a phase shift. And here's what an equation always looks like if you were going to move the graph left or right. You have to look for two things. The first thing you look for is, what are you doing? The second thing is, where are you doing? If you can answer those two questions, it will tell you the type of transformation you're doing. Any problem that involves a shift, whether it's moving it up and down or left and right, will always involve addition or subtraction. Shifting is always addition or subtraction. If you specifically do the adding or subtracting inside the parentheses, that makes it a phase shift. Adding or subtracting inside parentheses makes it a phase shift. Adding or subtracting outside parentheses would move it up and down. That'll be tomorrow. Alright, so that's a phase shift. That's subtraction inside the parentheses. That's a phase shift. You're adding inside parentheses. There's two things you have to look at. What's the operation? Okay, it's adding, so I know it's a shift. Okay, where are you doing it? Inside, or do you have something like this? That's different. That's adding, but it's outside. That'll be tomorrow. That's a phase shift again. Subtracting inside parentheses. And it can be sine or it can be cosine. The only difference between this and that is what table do you start with. If it's a sine problem, you need to start with the table on the left. If it's a cosine problem, table on the right. So follow these two rules when you're doing a phase shift, because we got to know, wait, is it left or is it right? You know it's adding and subtracting. Does anybody have a guess which one would shift it to the right? Do you think adding would shift it to the right, or do you think subtracting would shift it to the right? Yeah, right?
I think adding would shift it to the right and subtracting would shift it to the left.
So you would think, because on a number line, make a number line, positive numbers go to the right, negative numbers go to the left. Okay, you would think adding would move it to the right. Well, let's look at an example. Let's take cosine x. And let me take cosine of x plus, remember this is going to be in radians. So I'm going to shift it a small amount by adding, and let's see which way it moved. Let's do pi divided by 4. Pi divided by 4 is 45 degrees. So I'm doing a 45-degree shift. Well, you'll see which way in a second. So blue is the original, red is the shift. And let me do mode, put it in radians. So blue is the original, and red is the shifted one. Which way did the red one move? The red one moved to the left a little bit. So when I added something, it actually moved the graph to the left. If I take that same thing and let's subtract the exact same amount, pi divided by 4. So this one in black is going to be subtraction, and watch what happens here. The one in black moved to the right a little bit. So when you add, it moves left. When you subtract, it moves right. Not what you would normally expect. All right. Here's what we just kind of discovered. If you do x minus whatever the value is, it's going to shift it to the right. Minus shifts it to the right. How much does it shift it? Well, it depends on what number you put here. The bigger the number you put, the more of a shift that happens. And then if you do x plus a value, plus will shift it to the left. So out of the 4 transformations we're going to learn, 2 of them are what you would expect to happen. Like when we do vertical, plus is going to shift it up, minus is going to shift it down. Kind of makes sense. 2 of them make sense, and 2 of them are the opposite of what you would think. This is one that's the opposite. So you can make a reference sheet. So on there, you want to put the formula or write down whatever you need to, so you don't accidentally do every problem wrong, like shift it the wrong way. All right, so in general, think about if you're shifting something left and right. Think about something simple. Just think of a single coordinate. If you move a dot left and right, what part of the coordinate is going to change? The x value or the y value? If you move something left and right. The x is going to change. So what that means, when we want to find where the 5 original points in those tables I gave you, how they're going to move, the y's aren't going to move. If you're shifting left and right, the y's will stay the same. Where are you going to get the y values from? The 2 original tables that I gave you. Either the sine table or the cosine table. Just look at the problem you're doing. So the way a problem like this would be set up on the test is I'm going to give you a table, and it'll look just like this. Right? And there'll be 10 blanks. And you're going to fill in all 10. You're going to make a new table. Well, if you know the y's are going to stay the same, all you have to do to fill in the y's is look at your original table and copy the same numbers down. If you know what column stays the same, that's an easy 5 points. This table would be worth 10 points on the test. 1 point for each y, 1 point for each x you get right. So, shifting left and right, the y's stay the same, but the x's are going to change. How do we figure out the new x's? Well, first thing is you look at your problem, and you look at what has been added or subtracted inside the parentheses. So like in this case, you minus pi over 2. That's subtracting pi over 2. Now, what did we say about subtracting? Which way does the graph move when you subtract? it moves to the right. Think about if you had a coordinate and you wanted to move it to the right. We know the x value would change. What happens when something moves to the right? What happens to the x value?
It's positive.
So compare, like, let's say you had a point originally, and then you shifted it to the right, and you look at that one. How would the new x value compare to the old one? It would be greater. The only way to make something greater is to add. So when you have a subtraction problem or an addition problem, you have to do the opposite of what you see. And that has to do with the fact that it moves in the opposite direction that we would expect. So you look at your problem. If you see, for example, a minus pi over 2, what you're going to do is a plus pi over 2 to all of the original x values. Now, I'm not saying you're going to do the opposite for every single thing we learn all week, but for today, yes. Look at your problem, look at what's been added or subtracted, and then do the opposite. Because phase shift is one of the transformations that's the opposite of what you would expect. All right, so I think at this point we really just need to kind of go through one and see how it works. So let's look at this one. So on the test, all the different kinds of problems are going to be mixed together. So step 1 is going to be figure out what kind of transformation it is. Can somebody tell me why this is a phase shift? Two things you have to tell me. Yep, right.
Well, the subtraction side is inside the parentheses.
Yep, so there's 2 things. What are you doing? Subtracting. Where are you doing it? Inside. When you subtract inside, that's a phase shift. Okay, so what I did is I copied down the original table from the notes I already gave you, and next to it, I'm going to make the new table. Okay, when we do a phase shift, what values stay the same? The y's. So we can copy the y values down from the original sine table. Make sure you don't do the cosine table, sine table. So that's 0, 1, 0, -1, 0. If you get that, that would be worth 5 points out of the table right there. That's half the points. Now, what I do is off to the side a little bit, leave yourself a little bit of room. Put the original x values over here, because then we're going to do something to all of them, so you need a little space to do it. So the original x's are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, first of all, am I going to add something to all these x values or subtract something? All right, so what are we going to be doing here? Adding something or subtracting? Adding. So we're going to add something to all of them. This adding is going to cause them all to shift. Now, what are we going to add to all 5 of those? Pi over 2. So add pi over 2, pi over 2, pi over 2 to all of them. Once you do that, what's in that box is what I'm going to be grading. So I want to know all these answers. All right, so we're not going to use any decimals. Okay, we're just going to add them up. So that means usually your answer is going to have a pi in the final answer. All right, let's start with 0 plus pi over 2. How about Dylan? What's 0 plus pi over 2?
Pi over 2.
Just pi over 2. Okay. Next one. Well, we have fractions. To add fractions, you have to have a common denominator. Well, you already do. 1 pi over 2 plus another 1 pi over 2. How much would that be before you reduce it? Yep, right.
Would it be 2 pi over 4?
So when you're adding, you keep the denominator the same. You only add the numbers in the top.
Oh, so just 2 pi over 2.
It would be 2 pi over 2. So what I'm going to do, actually, I'll leave myself a little more space. That's 2 pi over 2, but then when we reduce it, it's just pi. I wanted to write it as 2 pi over 2 for a second because I want you to notice something when we're done. All right, the next one. Pi plus pi over 2. What's the denominator on this right now? 1. Do we have a common denominator? No. So the first thing we have to do is make this with a denominator of 2. And you do that by multiplying the top and the bottom by the same number. Anyone see what you would multiply the top and the bottom by? Yep. 2. Now we have 2 pi over 2 plus 1 pi over 2. How much is that? 3 pi over 2. Next one already has a common denominator. 3 pi over 2 plus 1 pi over 2. What would that be before you reduce it? Yep. 4 pi over 2. And once you reduce it? 2 pi. Now, what I want to do is just see if you notice a pattern at this point. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. How about the last one? So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. That would be the last one. And we figured that one out just by looking at the pattern. Basically, if you have everything with a denominator of 2, it goes up by 1 each time. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If this table was going to continue, the next one would be 6 pi over 2, then 7 pi over 2, 8 pi over 2. It's not as easy to see that pattern once you reduce it. That's why I wanted to show it to you before you reduce it and after. You should reduce it. It's just not as easy to see the pattern. All right, so there are your x values. Okay. Now the last thing is the sketching. Now, when you set up any type of graph, the only requirement when you label your axes is that you use things that are equally spaced. If you want to go by 2s, you can set up a graph going by 2s. I'm not going to go by 2s. If you want to set up a graph that goes by 5s, you can go by 5s. You just have to use things that are spaced equally. You can use anything you want. Think about our original table for sine. I told you these x values in degrees earlier. 0, 90, 180, 270, 360. These are all equally spaced. We started with values that were all nicely spaced. And we took all those values and shifted them all the same amount. If you start with values that are equally spaced and you move them all the same amount, are they still equally spaced? Yeah. It's kind of like if you had these points, and I asked you, are they equally spaced? And you say yes. All right, move them all to the right. Are they still equally spaced? Yeah. We started with something that we equally spaced, and you moved them all together. So because these numbers are all equally spaced, I would use those numbers to label your x's. So this would be 0. The next one would be pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. I put my labels down from the line a little bit because I'm going to be drawing in here like that. If I put my labels up higher, I'm probably going to draw right through them. All right. So now I'll enlarge that again so you can see it. I just need to see my points. So pi over 2, I'm at 0. Pi, I'm at 1. 3 pi over 2, back to 0. 2 pi, I'm at -1. And 5 pi over 2, I'm at 0. Let me zoom back in. So those 5 points give me a pretty good idea of what it should look like. Remember, when you sketch it, it should be a curve. Your graph should never do something like that. Okay, it should be always nice curve. So you go like this, and there's your sketch. See if I can draw that a little better. That's good. So that's your new one. And the original one would have looked like this. You don't have to do the original, I'm just showing it to you. So the new one has been shifted to the right of the original. Okay, any question on that? So that's a phase shift. So that's a phase shift with sine, and this one moved to the right. Let's try one with cosine, and now it's a plus. This time, I'm not going to write down the original table separate. I'm just going to build that table into my final answer. Okay, so first thing, what makes that a phase shift? Can someone tell me the two things you're looking for? Ellie?
You're adding them inside the parentheses.
Yeah, adding makes it a shift. Inside makes it specifically horizontal. What column stays the same when we shift something left and right? The y's. Can somebody remind me, what are my y's? Make sure this time you get them from the original cosine table. Yep, 1, 0.
0 and 1.
1. Okay, so there's your y values. Now, leave a little bit of space. You're going to put the final answers in that box. Off to the side, let's put the original x's. What are my original x's for cosine or sine? They're exactly the same.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Yep. All right, and now, next thing to figure out is, are we going to add something to those, or are we going to subtract? So we're going to subtract. And what are we going to subtract from each one of them? Pi. So this is a bigger shift than the last one. The last one was a shift of pi over 2. This one is a shift of a full pi. So it's going to shift it more. All right. Let's do the ones we can do quickly without common denominators. What's 0 minus pi? Yeah.
Negative pi.
Negative pi. Get that one. What's pi minus pi? I'm skipping to the third one.
0.
0. And what's 2 pi minus 1 pi?
Pi.
Pi. I just did numbers 1, 3, and 5 because I thought they were quicker. Now, pi over 2 minus pi. Tyler, what's my denominator here? Because there isn't one written right now. Yep, make it a 1. And we have to fix it so we have a common denominator. So, Mariana, what would I multiply top and bottom by? 2. Which I'll put the 2 in front. Because that's normally where you would put it. What's 1 pi over 2 minus 2 pi over 2? So think of it like this. Think of it as 1 over 2 minus 2 over 2. Yeah, this would be negative 1/2. Well, this is the same thing. It's negative 1, but it has a pi next to it, over 2. So negative pi over 2. Same thing here. That has a denominator of 1 times 2. Just going to draw right over it, times 2. What's 3 pi over 2 minus 2 pi over 2?
1 pi.
Over 2. There you go. So there's your table for the cosine. We started with x values that were all equally spaced, and we shifted them all the same amount. So they're still equally spaced. Use these as your labels. So we've got negative pi. That's this one. Negative pi over 2. I should have put my labels lower. That's good. 0, you don't have to label 0. I know the axis is always 0, but you can if you want. The next one is pi over 2. And this one is pi. If you want to put in the labels for the y-axis, you can, but you don't have to, because I'm going to go by ones. If you don't label a graph, it's understood you're going by ones. But this technically is 1, and that's negative 1. All right, and grab your points. 1, 0, negative 1, 0, 1. 1, 0, negative 1, 0, and 1. This is the graph most people mess up on the sketch because they draw it as a V shape. Remember, we're graphing waves. What you're graphing here is this. You're graphing the middle part of the wave. So it shouldn't be a V. It should have a curve to it. So just try to do it the best you can. Kind of like that. And then we continue on if you're going to keep going as we continue on. Okay, any questions on that one? All right. Last one. So one more phase shift. This time back to sine. And we're going to shift by pi over 4. So you might have noticed the amounts that we generally shift by are pi, pi over 2, and pi over 4. That corresponds to a 180 degree, 90 degree, and 45 degree shift. Could you shift by 37 degrees? Sure. You can shift by any amount you want. It's just 90, 45, and 180 are the most common. And those are the ones we'll do. Okay, let's make our table. All right, we should already know why it's a phase shift. What column stays the same? Yep. Y. And what are my original y values for a sine graph?
0, 1, 0, -1, 0.
Yep. Now I need my original x values, and I'm going to put those off to the side. What are my original x values?
0, pi over 2, pi, 3 pi over 2, 2 pi.
Yeah. By the end of the week, you'll know those because they're always the same. Every problem. All right. Add or subtract all of those. Add. And how much are we going to add? Pi over 4 to each one. Okay, first one, well, pi over 4. When you add something to 0, that's easy enough. Okay, next one, pi over 2 plus pi over 4. What do I have to do to be able to add those two up? Yep.
Get a common denominator.
I need a common denominator. You're only going to have to change one fraction. One of those numbers is fine. But what is the common denominator between 2 and 4? 4. So we're going to double the top, double the bottom. What's 2 pi over 4 plus 1 pi over 4?
3 pi over 4.
3 pi over 4. Okay, the next one, pi plus pi over 4. Okay. What's my common denominator there?
4.
4. Multiply the top and the bottom by 4. And what do you get when you add those two?
1 pi.
Yeah, very good. Now you can continue doing this. You can find the common denominator and add them up. But looking at the pattern, does anyone think they see what the next one would be?
7 pi over 4.
Yep, 7 pi over 4. And the last one?
9 pi over 4.
Yep,
Is there always a pattern?
always.
Okay.
As long as your denominator is the same, that makes the pattern easy to see. 1, 3, 5, 7, 9. It's going up by odd numbers. So once I find the pattern, I just go with that. But I usually do at least 3 to make sure I have the right pattern. Okay, questions on the table? All right, now, I want to think about a number line for a second with these numbers on. 1, 3, 5, 7, 9. Because it's basically what we have. If I was going to put this next point on the number line, where would the 1 go? Oh, no?
Not sure.
Where the 1 would go? Well, you see where 0 is.
Yeah.
Okay. So
Just the next one over.
the next one over. Now, do I always go the next one over in this case? Why not put the 3 right here? Just the next one over.
Because you're going by increments of 1, so you have to skip over for that to be 2.
Right, I have to skip 1. And the reason I have to skip that is because that's a 2 and I'm not using 2. And the next one is 4 and I'm not using 4. So I would put this next label at 5. This one would be 6 and that one would be 7. We're going to have to do exactly the same thing when we set up our fractions with pi. Most people see it easier when I just do numbers, but you have to skip. Okay, so let's set ours up exactly the same way. In fact, I could just use this really. So this is 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, skip, and go to 9 pi over 4. So if you get confused, just set your number line up without the pi's, and then just add them in, just like that. All right, need my y-axis. 1. That's a really bad spot for those labels. I should move them all down. I'm just going to draw over them this time. And now plot your points. 0, 1, 0. 7 pi over 4, we're at negative 1. Back to 0. Yeah, that's okay. That's fine. All right, so that's skipping things. Sometimes that trips people up a little bit. But my suggestion is just do it with numbers. Forget about the pies and set it up that way, and then just add all the pies in after, just like I did. Any questions on that? All right. So homework tonight is a worksheet. I think it's five questions, and the worksheet is on Schoology, and I'll show you where it is right now. So if you go to Phase Shift, click on the Phase Shift PDF, click View, and there's a spot in the homework for you to sketch the original sine graph, which looks the same for every sine problem, and then the new one. So I want you to sketch the original sine graph, which again, that'll look the same for every problem. And then on the right, sketch the new one that you get by shifting it pi over 2. And then on the back, there's a cosine, and a cosine. That's it.